Alright, so in this video, we're going to be talking about Gauss's law. Now, Gauss's law was definitely a more difficult topic when I was in Physics 2, which is also called electromagnetism. It definitely was one of the more challenging topics. I know that most of my class was struggling with that. So I want to give you guys a really in-depth just tutorial on Gauss's law, on just using Gauss's law to find electric flux, to find electric fields. I want to show you guys some different applications. So without further ado, let's jump into this. So here's the rundown of what we're going to be talking about in this video. The first thing I want to kind of address is what is electric flux. If we can establish a good idea of what electric flux is, then we now are going to be able to better understand what it is that we're actually finding with Gauss's law. Next, we want to talk about how to find electric flux. Okay, we're going to talk about some pretty basic examples of how to find electric flux, and then we're going to kind of get more complicated with it. Okay, we're going to kind of talk about different angles. We're going to talk about, of course, electric flux through an uneven surface, things like that, and we're then going to derive Gauss's law. Okay, so once we derive Gauss's law, then we're going to talk about what we just did actually means, and then I'm going to give you the final form of Gauss's law. Okay, then after we kind of finish the whole understanding of Gauss's law, we're going to dive into, of course, the applications, the problems, the stuff that you guys are actually going to be doing for your grade, right? So we're going to start off with creating a Gaussian surface. Now, this is pretty much how you solve all of these Gauss's law problems, is you have to actually create this thing called a Gaussian surface, okay? And we're going to do that for a bunch of different examples. First, we're going to do that through the electric field through a sphere, or for finding the electric field through a sphere. We're going to do that for finding the electric field for a line charge, and we're going to do that with, lastly, the electric field from a plane of charge. So we got a lot of stuff to cover in this video, so let's get started. First, we want to talk about what electric flux actually is. So say you have a point charge, okay? It emits its electric field in all directions, okay? Now, those electric field lines, okay, say you have some object with area A, okay? Has some area A, and that's the object right here, okay? And it has these electric field lines going through it, okay? Now, the electric flux, okay, right down here, the electric flux is the number of electric field lines that intersect a given area. Okay, so for that area, if we don't have as many field lines, okay, let's say we only have one going through that area, our electric flux is going to decrease, okay, because there's not as many field lines going through that given area. Okay, so if you understand electric field and you understand kind of the diagram here, then you easily can understand electric flux. Okay, and we're going to be dealing a lot with that in this video, so it's good to definitely understand what electric flux actually is. Okay, so that's electric flux. Now, how do you find electric flux? Well, basically, we need to at least understand what the symbol is for electric flux, because I'm going to throw that symbol in there a lot this video. The symbol is an uppercase phi, okay, and it's usually denoted with a sub E. All right here, the sub E, to denote that it's electric flux. There's other kinds of flux that we'll talk about in later videos, but now we got to actually talk about how to find this. Now, in the case where I just drew it above, you have a figure like this, where you have just a straight up and down some kind of boundary, some kind of surface, and you have electric field lines running through it, okay, and it's perpendicular. The electric flux is equal to just the electric field times the area. Okay, so that's literally it. That's how you find the electric flux when the field lines are perpendicular to some surface. Okay, it's just E times A. Now moving on, let's get a little more complicated here. What happens if the field lines are at an angle? If the field lines are at an angle, as you can see in this diagram right here, what's going to happen here? Well, we're still going to have that E times A, but now we're going to multiply by cosine theta. Okay, and that theta is going to be the angle in between that surface and the field lines. So let's pick a color here, and let's kind of show that here. So it's kind of this angle in between the surface and the field lines. So that's your theta right there. Now, let's get into kind of more of the, we're going to get a lot more rigorous here. Okay, so just try to stick with me for this. We're eventually just going to end up with an integral, but we got to actually work up to it. Okay, so if we have some random surface, okay, we have some electric field vector at any given point on the surface. We have some little electric field vector. We have some angle between the electric field vector and the area vector, which I'll talk about that as in a second, but just know that we're still dealing with the angle here. We have this area vector. Okay, now what the area vector is it's just representing, the magnitude of it is just the area, right? And the direction is just perpendicular or orthogonal, normal, whatever you want to say, to the surface at that point that you're dealing with. Okay, so it's just a vector perpendicular to a surface that represents area. Okay, so all this considered, we know that the electric flux, okay, if we're talking about just at this point here, the electric flux at this point is going to be EI times delta AI, okay, times cosine of theta I. Okay, so and that makes sense. That's exactly what we just did in this this part up here. Okay, we just now have I's. That's really it, because we're talking about just some really small point here. Okay, now we're going to just continue on here and end up with our integral notation. We can kind of further elaborate on this, on the whole fact that your electric field I equals, I'll write it again, EI delta AI cosine theta I. We can, and you kind of have seen this before, what we end up doing here is we say that the electric flux, we add all these little i's up, and we just say that it's the sum of EI a delta AI cosine theta I. And using the properties of the dot product, we can rewrite this as the sum of all EI dot delta AI. Okay? Now that's just a property of the dot product. So if I have some, let's write it down here. If I have some AB, okay, or sorry, let's say A dot B, two vectors, that's equal to AB cosine theta. Where here it's just kind of the magnitude of these vectors. That's a bad drawing here. Let me try something here. So I'll try to make it a little bit better. There we go. That's going to do. So it's the magnitude of those two vectors times cosine theta. So using that property, that's how I figured out I got from here to here. Okay, so now we can actually end up with our integral here, because of course with the sigma notation comes the integral, and that's just that the electric flux equals the integral of E dot dA. Okay, and that's that little delta right here. Okay, we're just kind of talking about that little change in area, right? So now this integral is a surface integral. Okay, it's the integral, it's going to be the integral over that surface. Okay, and this is denoted, I know in Calc 3 we kind of denoted this as S, right? We just kind of drew an S under the integral. But it is important to know that that is a surface integral, just because it makes sense with everything that we're doing here. And if you don't know what a surface integral is, not really a big deal. Okay, we're just gonna, and You don't need to. I didn't know what a surface integral was when I went through physics 2, and it didn't help. It doesn't matter at all because you're going to see in just a second here. So if you don't know what a surface integral is, just keep sticking with us here. It's not actually that big of a deal. Okay? And you'll see why it's not that big of a deal here when we derive Gauss's law. Okay? So with Gauss's law, we talk about closed surfaces. Okay? So we're talking about like putting a charge inside of a closed surface and finding the electric flux. That's a big part of what we talk about. Okay? And we know from electric fields that E equals, the electric field equals KE times Q over R squared. Okay? So that KE constant, right, times the charge over R squared. Okay? And that is for the surface of a sphere. That's what the electric field is for. Okay? So here's kind of where things are going to get a little bit tricky, but if you can stay with me, you're going to understand how to derive Gauss's law perfectly. Okay? So continuing on here, for a sphere, your electric field is always going to be parallel to your area vector. Okay? We know this because you have your charge in here, okay? Your area vector is going to be always your area vector is always going to be normal to your sphere, right? Or wherever that point is on the surface that you're talking about. And your electric field just goes out in every direction, right? And it's always going to be parallel to that area vector. Okay? So we know, and of course we know that E dot A is EA cosine theta. And since we know that these are parallel, we know that theta equals 0. So what do we get out of this? Well, we get that E dot A just ends up being EA cosine 0. And EA cosine 0, of course, cosine 0, that's 1. So we get the electric field times the area. Okay, so pretty simple, and that's why a sphere is so nice, and you're going to see that in some of these examples that we do. Okay, but we're going to continue on a little bit more here, and we're going to bring back the formula that we found. Where is it? Right up here. Okay, and we're going to now make it a closed integral. Where am I? Okay, right here. So we're now going to make it a closed integral. Okay, and again, if you don't know what a closed integral is, don't worry about it. We don't need it, and I don't need to really talk too much about it because it's just going to confuse everybody, okay? So the electric flux is equal to the closed integral of E dot dA, and now we can say that it's just E dA, right? We can say that this is E dA. We can get rid of the dot product idea because, as it is written up here, E dot A is just EA, so E dot dA is just E dA, okay? And, well, now E, that's just going to be, you know, some value that it's not going to matter here for the integral, because this is an integral with respect to A, not E. Okay, so we can take the E outside of the integral, and that's going to be really, really nice. Okay, so what we're going to do now is we're going to plug in that the electric field for a sphere is KEQ over R squared. Okay, so let's plug that in. We get that the electric flux is equal to, well, we have, instead of E, the closed integral of dA, we get KEQ over R squared, the closed integral of dA, which is going to be equal to KEQ over R squared. The closed integral of dA is just going to be A. Okay, just say evaluate it like a regular integral. It's just going to be A. Okay, and that is going to be equal KEQ over R squared times the area. Okay, when we say area, we're talking about the surface area. Okay, the surface area of a sphere is 4 pi r squared. So that's what we're going to substitute in for A. So we have that 4 pi r squared, and then you see that the r squareds cancel out. Okay, that's going to be important, so remember that. Okay, and we get 4 pi times Ke times Q. Okay, so setting, we're going to have this thing called epsilon naught. Okay, now this is the permittivity constant. Okay, you can kind of research more about what it actually means if you want to, but since we have this 4 pi Ke, okay, these are all constants, so we have just 4 pi times another constant, so we're going to make a constant out of that. And we're going to say that E naught is 1 over 4 pi Ke. Okay, so basically what we have here, and if you simplify this down, is that the electric flux is going to equal this Q right here. It's going to equal Q over that E naught. Okay, because we'll just have, and I can kind of prove that to you down here if you want. We have Q times, we have Q over epsilon naught, which is 1 over 4 pi Ke, right? And that's equal to Q times 4 pi Ke, which is what we have right here. Okay, so that's it right there. Okay, all you need to really know from this is that your electric flux equals Q over epsilon naught. Okay, so with that, we need to talk about what this means. Okay, because we just kind of derived Gauss's law, and we're going to show you I'm going to show you the final form in a second here, but we actually have to figure out what we just found. What does it actually mean? Okay, so let's figure that out. Now think about it. Okay, what did we just cancel off here? What did we just cancel? What did I say was going to be important later? Well, remember, we canceled off these r squareds right here. Okay, we canceled out the radius. So basically, you know, Q over epsilon naught doesn't have any r's. Okay, and of course remember that this is the electric flux. Okay, so it doesn't have any r's. So what this is saying is that the net flux through any closed surface surrounding a point charge Q is independent of the shape of that surface. Okay, so it doesn't matter what kind of shape you have for a surface. Let's get to that example that we talked about before. Okay, where we have, where was it? Up here. Okay, we have some point charge in this surface. Okay, it does not matter what the shape is of the surface. It's kind of really disgusting, right? You see all this grossness right here. Okay, it's going to have the same flux as it would if you just had a sphere. Okay, that's the idea. And that's kind of what Gauss's law is actually telling us, right? So it's kind of cool to see that, right? Radius, the radius actually doesn't matter at all. What that means is that the shape of the surface doesn't matter at all. You just have any sphere of any radius and you're going to get the same electric flux, okay? So now on to the final form of Gauss's law. Okay, the final form of Gauss's law is that the electric field, or electric flux, my bad, is equal to the closed integral of E dot dA. And that's the first thing that we kind of talked about and proved. And we know now that this is equal to the charge enclosed over epsilon naught. Now, if you're wondering why I have the charge enclosed there and not just the charge, why was there the in now, it's because if the charge was outside that sphere, well, all of the electric field lines that go into that sphere are going to come out of that sphere. So, whereas, actually, let me draw that. Whereas you have a charge here, you have some surface here. Whereas maybe you have positive flux here, okay, so you have some positive electric flux. Here it's just going to be minus that same electric flux, okay, and all these are going to end up canceling each other out, so what you just get the flux is equal to 0, okay, because everything cancels each other out. That's kind of the long story short, All right. So if you have the charge outside the sphere, you get an electric flux of 0. Okay. So we just talk about the charge enclosed. Okay. And you're going to see that in the examples why that matters so much. Okay. So now that you can understand what Gauss's law kind of actually is, where it comes from, right? Now we're going to actually get into some applications. And these applications, they're not just going to be like, regular problems with just like regular numbers, like we're talking about 30 coulombs of charge or something like that. I'm not really talking about that. I'm going to give you some really general examples. Okay? And from these general examples, you're going to be able to do, pretty much any Gauss's law problem that gets thrown at you, okay? Because I'm going to give you the intuition. That's kind of what the goal is right now, okay? So we're going to talk about the electric field through a sphere, okay? So we're going to be finding the electric field through a sphere right here. And let's just talk about this question right here. So a solid sphere has a uniform volume charge density. We're going to call it rho, okay? And that's what actually the notation usually is, at least for me. Hopefully it is for you too. So it's the volume charge density is rho and has a total charge of plus q. Okay, so it's positive. And it has a radius of d. Okay, so now what is E for a point outside the sphere? So what's the magnitude of the electric field for a point outside the sphere? Okay, that's the first thing that we have to find. The next is what is the electric field for a point inside the sphere? Okay, now here we're going to have to create something called a Gaussian surface. So remember how we had that sphere from before? Okay, we were talking about the electric flux through a sphere. Okay, well we're going to be creating a kind of like a fake sphere, okay? And that's actually going to help us solve some of these problems, right? Kind of sounds a little weird, but I promise it's not as bad as it seems. Let's keep going. So let's start off with finding the electric field for a point outside of the sphere, okay? Now I have the original sphere that we're dealing with, okay? That's in red. So this sphere, altogether, this whole thing, okay, this whole thing in here has a charge of plus q. Okay, so it's not like a point charge, it's a whole sphere with a uniform charge density. So the whole thing has charge q. Okay, and the Gaussian surface that we're creating is going to be a sphere with some larger radius. Okay, so it's going to be kind of this whole thing, and it's going to encompass that original sphere in red. This is a cross-sectional view, by the way. Just to kind of give you an idea of what we're doing. I'm not good at drawing spheres, okay? So remember that original sphere has a radius of d, and our Gaussian surface that we're going to make is going to have a radius of r, okay? And it's going to be going out to some point P, okay? And that's the idea. So why are we making a sphere? What's the whole idea of this Gaussian surface here? Well, the reason why we're doing that is because the flux, okay, the flux, actually, sorry, the electric field, my bad, yes, definitely, the electric field is going to be the same at any point that's, that radius away from the center of that original sphere, okay? So if you go anywhere around this entire circle, okay, the electric field is going to be the exact same. Right, the electric field is emitted equally in all directions. So, that being said, that's why we're creating a sphere here, because we have symmetry. That's the whole idea of Gauss's law. We have symmetry. Okay, so now we're going to use Gauss's law to find the electric field. So how do we start off with that? Well, we know that, actually, let's scroll right here. We know that the flux equals the closed integral of E dot dA, and we know that that's equal to the charge enclosed, which you'll also see it written as this little ENC, enclosed. You may not see it written as in. Okay, so the subscript may differ, but it means the same thing. And we also know that E and dA are parallel, right? Because this is a sphere that we're dealing with. Remember up here, where do we go here? Right here. We know that E and A are parallel. E and dA will be parallel as well. Okay, so moving on, we know that we're going to have the closed integral of E dA cosine of 0, right? Because the angle between these two things is going to be 0. Okay, and that's going to equal, the charge enclosed is Q. Okay, it doesn't matter that this is like a whole sphere that has charge. Okay, we're still going to treat it as a point charge. It doesn't really make any difference. Okay, so our charge enclosed, what's the charge that we're enclosing inside the sphere? It's Q, right? It's that plus Q that we had in the original problem. That was a given. Okay, and that's going to be over epsilon naught. So let's simplify this. Okay, let's keep going. Let's whittle this down a little bit. We have, this is going to be E, the closed integral of dA, and that's going to be equal to Q over epsilon naught. Okay, because we're just going to have cosine of 0, that's 1, and this integral is not dependent on E, it's dependent on A. Okay, so we can just take the E out of the integral. So the integral of dA is just going to be A. Okay, so we have EA equals Q over epsilon naught. And remember what I said that the area, the surface area of a sphere actually is. It's 4 pi r squared, right? So we're going to actually substitute that in here. So we have that E times 4 pi r squared equals Q over epsilon naught. Okay, and a very important thing to remember here. Okay, remember, epsilon naught is 1 over 4 pi times KE. Okay, because now look over here. We have a 4 pi. Okay, so if we have a 4 pi right here, okay, or not a 4 pi right there. If we have if we substitute in what epsilon naught actually is, all that stuff kind of goes up to the numerator. So that 4 pi is going to end up getting canceled. Okay, so let's actually see let's see that in action. Okay, we get E times 4 pi r squared equals Q times 4 pi KE. Right, if we put a 1 over 4 pi KE in the denominator of that fraction, like, if we substitute in 1 over 4 pi KE, like I said, all that stuff is going to go up to the numerator. So we have Q times 4 pi KE. The 4 pi's cancel, and we're just left with the electric field times r squared equals Q times KE. Okay, and now we just got to put that all together. And by that I mean divide by r squared. We get that E equals Q times KE over r squared. Okay, so what we just found is the electric field for basically if you're outside the original sphere, okay, any certain radius. All right, that's as long as that, of course, the radius that you're talking about is larger than the radius of the actual original sphere. Okay, as long as it's larger, you're fine here. But for any point outside that original sphere, we can find the electric field from this equation. Okay, and that's actually pretty cool. So now, a variation of this problem might be you're given the values. Okay, sorry, actually, to make the problem more specific, you might be given values. Okay, and in that case, say you're 5 meters away, okay, and the sphere is 3 meters long, or something like that. Now you are just plugging in and getting your answer. Okay, I mean, really, all they have to give you is the charge of the sphere, okay, in coulombs, whatever, and they give you the radius of the original sphere, and then they give you the how far away you are from the sphere. And you can find the electric field, right? So you have the charge, the radius, and of course you just have a constant right here. Okay, so that gives you your electric field. Okay, so there is a second part to this problem, and it's for a point inside the sphere. Okay, it gets a little more difficult. So here I have the original sphere in red again, okay, as it was before. So the original sphere is right here, and now we're at some point inside the sphere, okay, and we're going to make some Gaussian surface again, because of course any point along this surface here, the electric field is going to be the same. Okay, we're the same radius away from the center of the original sphere. Okay, and since the reason why, again, we're able to do this is because there's symmetry, right? Electric field is emitted equally in all directions. Remember that diagram I showed you in the beginning. Okay, let me show you that symmetry again. Scrolling way back up here, right here. Okay, you can see that it's emitted in all directions equally. That's why we're able to do this. Okay, you can be at any point on this sphere. Okay, and that's a terrible looking thing, but you can be at any point and the electric field is going to be the same because you're the same distance away from that point charge. Okay, going all the way back down now. All right. So, anyways, here's the big thing. Here's kind of the big difference here. Not all of the charge of that original sphere is going to be inside our Gaussian sphere. So our charge is going to be different. It's not going to be just plus q. Here's how we find the charge. The charge, okay, enclosed in our Gaussian sphere is going to be, well, remember we know the uniform, the volume charge density, okay, and that's rho. So multiplying that by the volume of the Gaussian sphere that we have, okay, or of the Gaussian surface, that's going to give us just the charge, okay? That's just going to give us the charge. Here's how I know that. Think about the units of charge, coulombs, right? Coulombs is going to equal, what's the units of the uniform volume charge density? It's coulombs per meter cubed. What's the units of volume? It's meters cubed. So you see the meters cubes cancel out, and we get coulombs equals coulombs. Okay, so that's pretty powerful here. Okay, because that's going to allow us to actually solve this problem. So moving along here, okay, if we kind of plug in, kind of using the same equation that we were before, we get EA equals, instead of, so we have Q enclosed over epsilon naught. We know that that is rho times V over epsilon naught. Okay, and we can plug in here with the surface area of a sphere, which is 4 pi r squared, and that's equal to rho times V. Again, plugging in what epsilon naught actually represents, it's 4 pi times Ke. Okay, we cancel off, not Ke, sorry. We cancel off 4 pi, okay, and we are just left with that the electric field equals rho times V times Ke over r squared. Okay, so r squared is going to sit in the denominator because it's over here. It gets divided over, of course. So now, what's the volume of a sphere? We can kind of even make this, we can simplify this even more. Okay, so here's how. The volume of a sphere is 4/3 pi r cubed. Okay, so we're going to plug that in. We have a Ke on the end, and we divide by r squared. Okay, and that is going to equal, simplifying further, we get 4/3 rho times it. We have the r squared cancels off with the exponent here, so we just have r left. So we have, I guess we can kind of write this as r pi. It's kind of hard to organize all the letters here, all the notations. But the last thing that we're going to do is substitute what the uniform volume charge density actually is in this case. Okay, so I'll write that out. So lastly, we substitute that rho equals, now here's how I figured out, or here's how we know what rho equals. Remember, it's the charge over the volume. Okay, it's going to be the volume of the original sphere, right? The original sphere has a radius of d, and remember the volume of any sphere is going to be 4/3 pi r cubed, and the radius here, again, I said, is d. So we're going to plug that in. Rho equals q over 4/3 pi d cubed. Okay, because remember, it's the charge over the volume, so I can even move this over here. and write the charge over the volume. So when we substitute that value of rho in, we get that E equals, well, now we can have a 4/3. I'm actually going to move this over because this is going to be a lot of stuff. We get 4/3 R times pi times, we have KE, that's going to be, and then we have over here we have Q over 4/3 pi d cubed. Okay, and we know that the 4/3 is going to cancel out with the 4/3 here. Okay, we know that the pi's are going to cancel out, and now we're just left with something a little nicer. We get RQKE over d cubed, and that's going to be for, you know, anytime where r is less than d. So when the radius of your Gaussian sphere, okay, is less than the radius of the original sphere, okay, so when you're inside the sphere, basically, that's how you're going to find the electric field, okay, and that's for any point inside any point, you know, some radius r away from the center of your original sphere. Okay, so that's pretty cool. So now we answered that question. So we found the electric field at any point outside the sphere and the electric field at any point inside the sphere. Okay, so now what we're going to find is the electric field for a line charge. Okay, so here we're not going to be using a sphere anymore, and it's kind of really interesting how this works. So here's the question: given an infinitely long wire with positive charge and a uniform linear charge density lambda, what is your electric field a distance r away from the wire? Okay, and we're talking about the magnitude of electric field because there's no vector symbol above the E. Okay, so here's the deal. We can't do a sphere here. Okay, a sphere isn't going to work because the wire is infinitely long. So here's what we do. We instead construct a different kind of Gaussian surface. We're going to talk about a cylinder. All right, so here is what we're going to do. We're going to draw our cylinder. Really hope this works out because I'm not the best at drawing. Okay, and then we have this guy, and maybe this will be straight, maybe. All right, sure, whatever. Now, the cylinder has the length L, and it has the radius. This radius is going to be R. Okay, so now here's what we can do with this. Here's kind of how we start off with this. There's two different components to a cylinder. Okay, there's the body of the cylinder, and then there's the ends of the cylinder as well. Okay, so we get something really nice off of this, and you can see that with the diagram below. Okay, somewhere on the body of the cylinder that we get that the electric field is going to be parallel to the area vector. Okay, so that means that the flux is just going to be E times A, right? It's going to be, you know, E times A times cosine of theta, which is theta is 0 here because they're parallel. Okay, so we get EA, right? So over here on the end of the cylinder, we get that dA is perpendicular to E. Okay, E is still going to be going away from the wire. So you're going to have the electric field's going downward, and the area vector is shooting out like this. So your electric flux is going to be 0. Okay, because, and I'll show you why in just a second here. If you're not familiar, if you're still kind of getting used to that whole dot product thing that I mentioned earlier. So for the ends of the cylinder, okay, we have that the electric flux equals EA cosine theta. Okay, and we know what's the angle here, the ends of the cylinder. This area is 90 degrees. So we have EA times the cosine of 90. Okay, and the cosine of 90 is 0. So we have EA times 0, that's 0. So there's no flux coming out the sides of the cylinder. Why does that make sense though? Well, because there's no electric field lines going out the sides, right? The electric field lines are always going down. So there's nothing going out the sides. Therefore, the flux is 0. And that just, if you understand the definition of electric flux, right? We're talking about how many electric field lines are going through a given area, right? Then you can understand this concept. So that's for the body, the ends of the cylinder. So for the body of the cylinder, we have EA times the cosine of 0, which is just EA. Okay, so by using this cylinder, we're making things a lot nicer for ourselves. Okay, which is it's gonna be really, really nice when we get down to our solving our actual problem. Okay, so moving on here for our solution, we know that the electric flux, we only really care about the body of the cylinder, right? And the body of the cylinder is just EA, because the ends of the cylinder, the flux is 0, so you can say EA plus 0 if you want, but it doesn't matter. So, and that's going to equal the charge enclosed over epsilon naught, right? Well, in the problem, we were given two things. We were, well actually, yeah, I mean, we were given the charge enclosed was, here we go. So we said that the linear charge density, sorry, that's what we were given. We were given those positive charge, and we were given there was linear charge density lambda. Okay, those were the two things, the two kind of main things that we're going to focus on here. So the uniform linear charge density is lambda, which means, going down to our problem here, much like we did before, where we had that the uniform volume charge density played a role in our actual charge. So it was, the uniform volume charge density times the volume. Here it's just going to be the uniform linear charge density times the length of the cylinder. Okay, so that's the charge enclosed of the cylinder. And we know that A, the surface area of a cylinder that we're talking about here, is just 2 pi RL. Okay, we're just talking about the body of the cylinder. We don't care about the ends, because for the ends the flux is 0, so it doesn't matter at all. Okay, so now we can plug all this in. So we're just gonna take these two things and we're gonna bring them down. So we have E times 2 pi RL equals the linear charge density over the length, times the length over epsilon naught. Okay, and coming down here, we're gonna plug in what epsilon naught actually is, and also you see that the lengths cancel off. So we get E equals, E times, well, actually, we can divide this over. So we get lambda over 2 pi r epsilon naught, which is the same thing as saying lambda times 4 pi ke over 2 pi r. Okay, and the pi's cancel off and we just get a 2 on the top. So we know that the electric field is just going to equal 2 ke lambda over r. So that represents what we just found right there. That represents the electric field any distance r away from that infinitely long wire of charge, okay, or that infinitely long line of charge, and that line of charge has some linear charge density lambda. Okay, and lambda is just, and again, if you're not comfortable with what that is, it's just the charge per meter. Okay, so it's the amount of charge per meter. That's what the linear charge density is. There's also the surface charge density, which is the charge per meter squared. And then you of course have the volume charge density that we talked about earlier. That was the charge per meter cubed. Okay, so if you're, hopefully that kind of makes sense to you now, if it didn't before. But there you go. So that is the electric field, any distance r away from the wire, and saying that the wire has some linear charge density lambda. Okay, so now we're going to move on to our last, our kind of third and final problem here, and that's the electric field from a plane of charge. So here's our problem. An infinite plane has a uniform surface charge density, and that's going to be sigma. Okay, so now you're going to get to deal with the surface charge density here. So we're going to get to deal with all the different charge densities. And it is positively charged. Find the electric field produced by this plane. Okay, so here's our plane right here. Okay, and here's the idea of what we're about to do. Okay, we're actually going to end up sticking a Gaussian surface through this plane. Okay, so we're actually going to be sticking a cylinder through this plane, and so it's going to be a lot nicer than a sphere, and I'm going to show you why. Here's how this is going to work. So here's how your plane. So we're going to take this plane that's right here. We're going to turn it sideways, and we end up with this. Okay, we stick a cylinder, which is in brown. We're going to stick it through the plane. Okay, and you're going to have all the electric field lines are just going to go perpendicular to that plane of charge, right? That makes sense. Here's the idea now. You're not going to have any electric field lines coming out the body of the cylinder, only out the two ends of the cylinder. Okay, so that's going to be really important here. All right, so that's really nice. So now we're only talking about the two sides of the cylinder. We don't care about the body of the cylinder again. And I could show that to you right now. Of course, you can see that the electric field is perpendicular to the area vector, so we're going to get zero flux. But it should, kind of make sense conceptually anyway why we would have zero flux, right? There's no electric field lines. So we can see that there's zero flux through the body. Okay, and now this is we're going to be allowed to solve this here. Okay, so we're going to find that electric field. Now we know that the electric flux is equal to the closed integral of E dot dA. We can say that this is equal to the charge enclosed over epsilon naught. And from that, well, what's our charge enclosed? Well, that's going to be equal to the surface charge density times what is going to be that thing. So we have the surface charge density is coulombs per meter squared. So that means that we're going to be multiplying by meter squared to get coulombs, which is the area, right? So it's going to be equal to the surface charge density times the area. Okay? When you do that out, you get, well, you're going to get 2 times EA. Okay, bring in this guy down. And the reason why I say 2EA is because you have two sides of the cylinder. Okay, you have two of the ends. All right. So instead of having just EA like we usually do, okay, we're going to have 2 times EA. And that's going to be equal to the charge enclosed over epsilon naught, which again, since I have the sigma A in there, we're just going to plug that in. We're going to have sigma A over epsilon naught. Okay, and notice we're not going to plug in what epsilon naught actually is in here because it doesn't really matter. We don't have any nice things that we can easily cancel off here. So what we're going to end up doing, we're just going to cancel out those areas. So we end up with 2 times the electric field equaling sigma over epsilon naught. And of course, dividing that 2 over, we get the electric field is equal to sigma over 2 epsilon naught. Okay, so that is our final answer. Now real quick before I we're all set. We end this video. Let's kind of review what we did, and then we'll call it quits, and you'll be free to go. Okay, so we start off with just what is electric flux. We defined electric flux as the number of electric field lines that intersect a given area. Okay, we talked about how to find electric flux if it's something easy like just kind of you're passing through some plane. Okay, the electric flux is just E times A. Okay, we made it a little more complex, adding in the cosine theta when the plane's at at an angle. And we talked about a random surface, and don't worry about the i's here. We just ended up with a surface integral, okay, of E dot dA. Okay, from that integral, we were able to derive Gauss's law, or we used it in. Well, actually, I don't think we did. Okay, we did use it. But we used it, we kind of started off with a sphere. We said E is going to be parallel to A, so we know that E dot A is just EA. Okay, we plugged in what we know that the electric field is for a sphere. So we found that our electric flux is just the charge times epsilon naught. Okay, and we talked about what it means. It means that the net flux through any closed surface surrounding a point charge Q is independent of the shape of that surface. So pretty cool. The final form of Gauss's law is, just that closed integral, okay, times the charge enclosed over epsilon naught, okay, and that's, Gauss's law is kind of giving us what the electric flux actually is, okay. So that's something there. Now we talked about 3 examples. We talked about the electric flux through a sphere. We talked about the electric field for a point outside the sphere. We talked about the electric field for a point inside the sphere, and we found all those by creating a Gaussian surface. Here, our Gaussian surface was a sphere. We were already dealing with a sphere, so it made sense. We have symmetry if we create a sphere. So whether you're creating a sphere or a cylinder, it all depends on what you have with the better symmetry, right? For the plane, the cylinder was definitely the way to go. For the line, of course, the cylinder is the way to go because that's how you have symmetry. But for a sphere, it makes sense to have another sphere. Okay, so if you can figure out which shape gives you that symmetry, you're perfect. So here's kind of all the work that we did, right? We just ended up plugging we plugged in the surface area, we plugged in the charge, we plugged in everything. We got that the electric field for any point outside the sphere was QKE, Q times the Coulomb constant over R squared. And we talked about a point inside the sphere where we're not dealing with all the charge. How we find that charge is by multiplying the volume charge density times the volume. Okay, and we kind of kept going here, and we just, after a bunch of work, mainly, just really algebra work, just plugging in different things, we got that the electric field for any point inside of the sphere is going to be R cubed times the Coulomb constant over D cubed. All right, we talked about a line charge. We talked about how we set up our cylindrical Gaussian surface. We talked about why we did it, because you can't do a spherical Gaussian surface when the wire is infinitely long. It doesn't make sense. We talked about how through the body of the cylinder, that's the only flux that we care about because there's no flux through the sides. Okay, so we only talked about the body here, and we used that to find the electric field. Okay, and that was just 2ke lambda over r. And then lastly, we talked about the electric field from a plane of charge. Here, we stuck a Gaussian surface through the plane. We talked about, again, a cylindrical Gaussian surface because that's what gave us symmetry. That's what gave us, something really nice. If we would have stuck a sphere through it, it really wouldn't have worked out as nicely. Okay, so we have zero flux through the body. We just only have it through the end caps, and we eventually kind of narrowed it down to the electric field equaling sigma over 2 epsilon naught. Okay, so that's going to do it for this video. Just a couple things before I go. Make sure make sure to subscribe for more. I'd really appreciate it, and I do appreciate all the support for those of you who are already subscribed. Also, check out the description for my full Physics 2 course. If I have it up, I should. Hopefully, by the time most of you watch it, I also we'll have a probably like a 100 question Physics 2 final review video. I have a Facebook group that I can link in the description for homework help, and I have my Patreon where you can just donate if you're not looking for any of this stuff. You just want to kind of help me out. You want to support what I'm doing. So thank you so much for watching. This took hours and hours to make, so I do really appreciate everything. Thanks for sticking through this thing with me, and if you have any questions, leave it in the comments down below. I'd love to help you out if there's anything that you were unsure about, any of the charge densities, any of the other stuff that we talked about, and anyways, thanks for watching. I'll see you soon.